This talk is joint work with Sasha Neshetov. And I'd like to thank the organizers for having given me the opportunity to speak, and also more generally for organizing this amazing seminar. Okay, so we're just going to start with some basic notation. We have a field, obviously, separable closure in the absolute Galois group. Totaro defined the Chow ring of a classifying space for an algebraic K group, and so basically the idea is this: we've got there exists a KG variety, KG scheme, and an open G invariant subscheme. And the codimension, we're going to assume codimension of S and V is greater than or equal to I plus 1, and then define Chow I of BG. Oh, I forgot to say something, sorry. Then G acts freely, so G acts freely on E minus S. And then it makes sense to define the Chow group to be the ith Chow group of this quotient. This definition is independent of B and S. And then you can define the Chow ring. And it's commutative and graded. Commutative. Okay, so there's been a lot of study of this over the years for split algebraic K groups. Totaro solved this when he originally defined this. He solved this problem for some of the classical groups, GLN, SLN, and SP2N. In these cases, these are polynomial algebras over in the Chern classes of the natural representation. As you go down this list, the descriptions get more complicated. So Totaro and I'm sorry, I cannot Pandari Pandi did it for the odd SO2n plus 1, and then it gets much more complicated for the even case. I'm not going to write down the description. So G2 was done by Yagita, and Vasozi did PGL3, and PGL-P was done additively by Vistali, and that's just basically to show that it's much more complicated. And then the natural question is, what about the non-split case? And if you're going to ask about the non-split case, it makes sense to look at tori because they're so simple, at least in the split case they are. The Chow ring in this case is easy. It's just a polynomial ring, or more precisely, it's the symmetric algebra over Z of the character lattice. And so then that ends up being isomorphic to a polynomial ring in our variables. So an algebraic K-torus, as you probably all know, is just a K form of a split one. Sorry, it's not right. And so then we want to look at a typical game to do when you have results about the split forms of algebraic groups. You might want to compare what you know about the split case with what you know about with the original K form, and you have a natural map. Given by base change. And then this map is neither injective nor surjective in general. But you can interpret the torsion part of Chow 2 as the kernel of this map. Okay, so Blindstein and Mercury have studied this torsion group, and did a lot of work on it. They first showed that it was finite. They gave good descriptions of it, but some natural consequences, finite and to torsion. And they produced some families of examples. They've made a way of computing it in certain way, in certain cases, and families of examples in which this was zero. And we'll talk about more of them about these later. And then the natural question is it possible to find something, a torus and a field in which this is non-zero? Okay, so we're just going to review some things that are probably well known, so we'll go quickly. So there's a natural correspondence between algebraic K-tori of dimension R to isomorphism and finite subgroups of GLRZ up to conjugacy, and that's given by a fairly natural map. Obviously, one cohomology has to come into play here, and so it should be indexed by Galois 1 cohomology with of the absolute Galois group in the automorphism group of the split form. But the split form in this case has a really nice automorphism group, and then that makes it fairly simple. Also, this is compact, and that's discrete, so we actually get continuous homomorphisms. So then it makes sense that we have finite subgroups of GL or Z coming into play. So then you can look at this at the level of instead of looking at it over the algebraic the separable closure, you can take a Galois splitting field and look at it at that level, and then you've got a finite Galois group, and you can look at the correspondence between algebraic K-tor that are split by this Galois extension up to isomorphism and the corresponding Z lattices, and there's a nice correspondence. You would do the natural thing, which would be to take the character lattice and then in the other direction, you can construct a torus by in this way, by taking the group algebra of the lattice, take invariance under the group, and taking spec of that. So that's the affine algebra. So it's natural to look at what, to what extent does the representation theory here to what extent does that give you information about the birational properties of the torus? So we need some lattice terminology. So their Coflask resolutions were introduced by Colliotilane and Sansuk. So a G lattice M has a Coflask resolution of this type where the P is permutation, P permutation. C is G Coflask, and that means that the first cohomology vanishes for all the subgroups. And of course, this is a short exact sequence of G lattices. And there's a certain amount of uniqueness here. This is determined up to stable equivalence, i.e. C is determined up to stable equivalence. If you had another such sequence, not that. as above, then this guy and C are stably equivalent, where this is a G permutation. So one defines oh, actually, I didn't want to do that here. Sorry. You can do that. So it's determined up to stable equivalence. So dually, you can make a Flask resolution, and here this is a permutation, and this is Flask, which is just the same thing, except the cohomology is with -1 coefficients. Sorry for all the subgroups. And again, it's determined up to stable, the F is determined up to stable equivalence, and one defines this invariant of the Flask resolution as being the stable equivalence class of the lattice F. Okay, so the reason why we wanted to introduce all of this is because, as I was hinting, that you have all these nice properties about nice birational properties that can be predicted by the integral representation theory once you have this set up. So if you take your algebraic K-torus that's split by L, and then take the Flask class of the character lattice, then you get all these nice results. Endomiata prove that T is stably rational. So then got necessary and sufficient conditions here. So by which I mean, if you tack on another torus, or you could tack on another torus, then you get something rational. That's true if and only if this is stably permutation. And this is retract rational. That's the definition of Saltman. And that means that we can factor the identity rationally through affine space, and that's detected by F is invertible as a G lattice, which means that there exists some complementary lattice such that this is permutation. And then Mercurys and Scavia, well, they did this in their each in their own way, or one was a refinement of the other. So for a prime P, they generalize, or Mercurys generalized this definition. So to P retract rational, and what does that mean? We have a dominant map here. And the degree is prime to P. So taking the place of the identity, and then this factors this. And so this is detected by F being P invertible, which is a nice generalization, which when it's all boiled down ends up being the same statement, but localized at P. So when this was originally worked out by Kolyotolain, Salsuk, and Voskresensky, they were thinking, they had a geometric construction of the Flask resolutions, and which is quite nice. You can, at least in the characteristic zero case, you can make a smooth projective model of P, and then you get a geometric construction of the Flask resolution by taking the character lattice, and then the permutation is permutation generated by the complement. And then the Flask lattice is the Picard group of the smooth projective model. So this is Flask. So this is very nice. Unfortunately, it's not always so easy to find a smooth projective model. And it's also true that that some resolutions that you can find algebraically cannot be achieved or not obviously achieved in this way. So, well, there has always been, I think, starting with Kolyotolain and Salsuk, they had an alternate algebraic approach to find to determine this. But Hoshi and Yamasaki produced some gap algorithms to do this when they were looking at their classification of stably and retract rational algebraic tori in dimensions 4 and 5. And so they produced some algorithms in gap to compute these resolutions, among other things. Because in general, it's not totally obvious. I mean, the algorithm is obvious, but it's not that easy to compute. So then Mercurys made a construction to compute Chow2 of BT. It's sort of a refinement of the work that Blindstein and Mercury did together. So, I mean, an algebraic refinement in that sense. So it starts out like this. If you have a G lattice, then mod out 2. This is the second exterior power on the end. And this one is sort of a mixed quotient of this. It's still a quotient of M by itself, but you're going to quotient out these terms instead. And then it was labeled as alpha M, comes up in this construction. It's just the connecting homomorphism for this sequence. Oh, I know what I forgot to define the maps. Yep, but the maps are fairly straightforward, and they would be what you would think they would be. So this is going to the image of the second of the tensor, tensor product of M with itself in gamma 2M, and then this would be that the other map would send this generator to the second exterior power. Okay, so then these map, the connecting homomorphism has some nice properties. It's fairly clear that if M is equal to permutation, which is obvious that it would be important in this setup, then the sequence splits. Which means that the map is 0. In that case, I should just say that. And then if you looked at the image, it works well with direct sums. Which means that if M and M prime were stably equivalent, then we get an isomorphism. So those are all useful properties. And so basically how this invariant is defined is it's not defined on the original lattice, but it's the image of the connecting homomorphism for M, which is the Coflask lattice in the Coflask resolution. And then, oh yeah, so it's independent of the choice of resolution. That would be an important property. it's fairly clear that 2 kills it. Oh yeah, that it vanishes on invertible or 2 invertible lattices. Two invertible is invertible, so I mean invertible. Yeah, the other way around. Invertible implies 2 invertible. Then you can say that also the restriction map is injective. Into the CO2 subgroup. And oh, I think it was just on direct sums. But we already sort of talked about that. It works well with direct sums. Okay, so so this was how he set up his invariant. And what's the point? Well, you can get you can determine the torsion part of Chow2 from this, not necessarily on the nose, but at least we have this, that it's a quotient. Which would mean that if this vanishes, the other thing vanishes. So that's pretty useful. And in a particular case, you can get equality, probably more than one, but this is one that works. If you have a faithful QG rep. And you take the field of fractions there, and the invariance, then you've got a Galois extension, and you actually have equality in this case. So Blindstein and Mercurys came up with some examples and classes of examples. So they have, by what we've already seen, if the dual lattice is to retract rational, then that's equivalent to it being the character lattice being 2 invertible, then this invariant vanishes. Also, if you've got the Veil restriction of scalars on GM, mod GM, whose character lattice is just the augmentation ideal of G, then they were able to show that vanishes in that case. And if the torus is split by a cyclic group, then it turns out that any Flask resolution, if you did a Coflask resolution, the Coflask lattice would be invertible, so it would satisfy condition 1. And by the integral representation theory of C2 cross C2, it turns out that that example 2 is exactly the problem case that needed to be solved, that wasn't solved by the other points. And so one can see that that this invariant vanishes in all those cases. Okay, so and I did not. Okay. I did not erase this. Okay, let me just. Okay. So Scavia produced an example in a very nice way. He produced an example of a lattice and a group, a 2 group, which didn't vanish. And it turned out that so she took the CELO 2 subgroup of a Suzuki 8 group, which turns out to have order 64. So his lattice has very large rank. However, the construction is very nice. It basically, he has a very nice idea. What he does is he takes a particular lattice that depends on G, and finds a Coflask resolution. And then he determines a condition on this guy. Is not 0. If he involved the Steenrod square, he reduced the problem to group cohomology with coefficients in Z12. So if the image of this map oops, that's not right, is not contained in a subgroup that's determined by so for each subgroup, it's determined by very natural maps. So here's the, this is a 2. Sorry, should go. Yeah, I shouldn't have given those details, but followed by the cup product. Oh, sorry, these should be H's. There's something wrong here. So for each subgroup, we have a sequence of maps into H3 Z mod 2Z, and then followed by co-restriction. So determined by the images of all these maps, the sum of the images of those maps. If it's not in there, then he could show that it's not 0, and then he produced an example that worked. But then the question is, could you make a smaller example? And that's what we're looking at. So this is just notational. If you have finite subgroups of GLN-Z up to conjugacy, there's this correspondence with G lattices up to isomorphism, as we've talked about before, and I'm just writing notation. So G is going to correspond to MG. And so Serre figured out the maximal two subgroups of GLN-Q. And it turns out that it's a fairly nice answer, that they are of the form CeLU2 subgroup of the Weil group of Bn, acting on, which I'm going to abbreviate as Gn, acting on Z. I mean, because we're on Q, Bn. So this is a sign permutation action. So that this is the restriction of the action of the Weil group of Bn, which acts by permutation and sign changes on the root lattice. And well, this is rationally. But then that means that if you have, so yeah, I said it acts by sign permutations. It's a defined permutation module. So if you have a subgroup, a 2 subgroup, then the group is going to be the subgroup of the CeLU2 subgroup of the Weil group of Bn, and you know that this is sign permutation after tensoring by Q. So sign permutation QG module. So it's a form, it's a Z form of a sign permutation. Although you don't generally know that much about Z forms of representations, in the case of a reflection representation, you do know that you have a Z, if you have a root system phi, then and you have a lattice on the reflection space, then it has to be trapped between the root lattice and the weight lattice. And this completely determines it. So in the particular case of the Weil group of Bn, which is a nice Weil group, acting by sign permutations, and then the lattices on QBn are what you would think. And in the small cases, some of these coincide. So it turns out that the maximal two groups of GL and Z are in some sense determined by all of these examples. That's not quite right. It's their direct sums. The lattices are direct sums of these. So, and I will make it more precise. So for n is equal to 2, it's quite easy. So this is my abbreviation for the CO2 subgroup of the Weil group of Bn, which actually has a nice formula. Do this, Sarah. I mean, you can define it inductively. So it's just the Weil. I mean, the lattice is just B2 in this case. All of them are isomorphic. In n is equal to 3, it's also easy. You just get that, and the lattice is either the root lattice or the weight lattice. In n is equal to 4, it's mostly that. And there's one funny example, but it's still not really that bad. It's still a direct sum. And then n is equal to 5 continues that pattern. So you get the 3 that you would expect. And then you get some decomposable cases. Again, not unexpected. But these are maximal. So these are all fairly well behaved. And the point is that although there are lots of subgroups of of these lots of two subgroups, the fact that these are the maximal ones means that you know what the lattice is by restriction of these nice lattices. And if you knew a Coflask resolution for these nice lattices on the top, then you'd be all set. You'd get a Coflask resolution for all of the cases below. And in fact, there is a nice natural Coflask resolution of the weight lattice of Bn. And that takes care of a lot of these cases in terms of the Coflask resolutions. So you can reduce to the two-group case, obviously, indecomposable lattice. And you can not worry about the sign permutations because those are actually correspond to rational tori. And so then you just have, for these cases, you just have to focus on for n is equal to 3 and 4, you basically only have to worry about the weight lattice. And for n is equal to 5, you have to worry about the weight lattice and the ZC5 to get Coflask resolutions of those. And so basically, Sasha made these really nice algorithms to compute all of these, to compute these invariants. He basically he basically reduced the calculation to one cohomology calculations. He also, in some cases, restricted it to a mod 2 setting. I'll just say this. The most interesting idea that he developed a Smith normal form for computing these one cohomology calculations over Z mod 2 to the n. Because the truth is that anytime you had to calculate with these subgroups of GLN GL6Z, the computations just blow up in a hurry, and he came up with this nice way to reduce the calculations. So in dimension 6, he completely computed all the possible ones where the invariant is non-zero. But I was interested in what do these things look like. It turns out that the fact that the maximal subgroups, the maximal two groups don't behave as well in dimension 6. They're not coming from, they're not all coming, most of them are coming from reflection arrangements. But I can write down this example. So this is the smallest example. Oh, by the way, the ranks are all in the counterexamples are all 1 with 3 exceptions in 3 cases. Rank is 2. But this example is not really that hard to write down. So this is the C2, and the C4 is a block diagonal matrix, and it's clear that these are of order 4. And the point is not that, but that this module, the lattice is still fairly nice, even though it's not what you might think. So these are signs, the plus or minus ones that have product 1, and if you think about it, the maximal 2 group here is the Weil group of D6 rather, which happens to preserve this lattice. But it doesn't act by reflections. Okay. That's all I have to say. Thank you very much.
Thank you. Thank you. Is there any question? Any question? So when you said for n equals 6, they're not all reflection. I mean, they're not all coming from reflection group. So, but can you identify? So
oh yeah, yeah. So for example, PGL2, like on the maximal level, not the 2 group level. So there's PGL27 cross C2 is the group. And I don't know how, I don't have a nice description of the lattice in that case. Most of the maximal, the maximal groups are still coming from root system information. But that's one counterexample, and this one is sort of funny. This example seems to cause some trouble, although it's fairly natural looking. But yes, I have a description of most of the maximals. I don't want to go through all those, but that I can describe the lattices for n is equal to 6 in most cases. And they're mostly coming from root system information.
Okay, thanks. More questions?
What is known about Chow groups in higher codimension for BT for torus?
I'm not sure that I don't know whether there's any work being done. None that I know, but it seems difficult enough for Codimension 2. But yes, that's a good question.
So is there any hope of expressing it in lattice theoretic terms, like in the case of Codimension 2?
I'm not sure, but that would be a nice thing.
More questions? Okay, if not, then but thank you, speaker. Thank you. And we will resume in a week.